Welcome to the AI Digest for 2026 W32. This week we'll cover two topics. Let's get started. As the automotive industry evolves, the need for advanced software-defined vehicles grows more urgent. An article by Panasonic Automotive emphasizes how their innovative vSkipGen platform is set to revolutionize in-cabin experiences in vehicles. This shift represents not just a technological upgrade, but a significant transformation in how manufacturers develop and validate cockpit software. Traditionally, developing cockpit software for vehicles has involved cumbersome and physically demanding processes. Manufacturers often relied on costly physical prototypes, which not only consumed time and resources, but also limited innovation. With the rise of software-defined vehicles, however, there is a pressing need to create a more flexible environment for rapid software development and testing. This shift is driving the need for scalable solutions that can keep pace with technological advancements. The introduction of Cockpit Domain Controllers, CDCs, presents a solution, acting as a central hub for in-cabin experiences. These controllers require sophisticated software that can be rapidly developed and validated in a hardware-independent manner. However, existing hardware limitations and the demand for high-performance graphics pose significant challenges, making it imperative for automotive manufacturers to adopt new approaches. To address these challenges, Panasonic Automotive's vSkipGen is positioned as a next-generation virtualization platform. Built on Google Cloud's C4A-metal, it allows teams to develop and validate cockpit software in a cloud-native environment. This shift enables manufacturers to innovate with fewer hardware constraints, ultimately leading to faster time to market for next-generation automotive solutions. C4A-metal is particularly noteworthy, offering up to 96 virtual CPUs alongside two robust DDR5 memory configurations, 384 GB and 768 GB. Additionally, it boasts networking bandwidth of up to 100 gigabits per second. These features are crucial for handling complex tasks, such as creating digital twins of vehicle cockpits, where performance parallels real-world behavior. Furthermore, C4A-metal's ability to deliver the high performance and hardware-level access characteristic of bare metal, combined with the scalability of cloud infrastructure, sets it apart. Panasonic Automotive can now navigate around traditional hardware bottlenecks, ensuring that teams can perform virtualization tasks efficiently and rapidly, enhancing the overall development process. Andrew Polyak, CTO of Panasonic Automotive Systems America, notes that Google Cloud's Axion bare metal has been a game-changer for our vSkipGen platform. This endorsement further emphasizes C4A-metal's role in reducing dependence on costly physical prototypes. The infrastructure facilitates the development of production-intent software with behavior that closely mirrors target automotive hardware, improving validation efficiency and increasing test coverage. By utilizing vSkipGen alongside unified HMI technology, automotive manufacturers can now construct, test, and validate complete Android automotive OS stacks in a cloud-native setup. This transition from physical dependency to scalable digital twins not only empowers innovation, but also streamlines the testing process, leading to more refined and high-quality products. The advent of solutions like vSkipGen and C4A-metal signifies a broader industry trend toward more agile development methodologies. As manufacturers increasingly adopt cloud-native platforms, we can expect accelerated innovation in automotive technologies, ultimately benefiting consumers with richer in-cabin experiences and better safety features. The automotive landscape is entering a new era defined by flexibility and rapid technological evolution. As the automotive sector embraces digital transformation through platforms like vSkipGen, the focus will remain on optimizing development processes. Observers should monitor how quickly these technologies are adopted across the industry and how they impact the future of vehicle software development. The shift itself may redefine competitive advantages as manufacturers seek to adapt and thrive in this evolving landscape. In a world increasingly reliant on digital services, ensuring application uptime is crucial. The recent advancements in Cloud Run's multi-region capabilities provide a simplified approach to maintaining high availability for mission-critical applications. This update addresses the complexities and manual processes typically associated with deploying resilient services across regions. Prior to these enhancements, managing multi-region deployments required intricate configurations. Businesses struggled to implement effective failover strategies, often relying on manual interventions that introduced potential delays and errors. These challenges were particularly critical for applications that needed to remain operational to secure a competitive edge and customer satisfaction. Core thesis of the article emphasizes that Cloud Run's enhancements deliver a streamlined, one-command approach to setting up multi-region services. This simplifies the deployment process while providing crucial functionalities like automatic health checks and failover mechanisms, ultimately reducing downtime and enhancing resilience for applications operating across multiple locations. One of the standout features introduced is the readiness probes. These probes perform instance-level health checks on Cloud Run services, allowing operators to determine precisely when their containers are prepared to handle traffic. This proactive approach to monitoring is crucial for minimizing disruption during outages, as it ensures only healthy service instances are serving requests. Additionally, the aggregated health data from these readiness probes is utilized to calculate overall service health in each region. This information is presented through serverless network endpoint groups, enabling organizations to clearly understand the state of their services. Such transparency allows for swift decision-making and enhances the efficiency of incident response strategies. The article also highlights how these enhancements allow for automatic failover functionality. When connected to a global external application load balancer, traffic is intelligently rerouted away from any unhealthy service instances. This capability ensures that users experience minimal disruptions, maintaining reliable access to services even when certain regions encounter issues. For organizations with public internet applications, configuring Cloud Run with a global external load balancer is essential for realizing these benefits. Conversely, applications that operate within a private network can leverage a cross-regional internal load balancer, tailoring the failover solutions to fit specific operational needs. This flexibility allows companies to design their infrastructure based on the type of application traffic they expect. Moreover, businesses operating multi-tiered applications should be cautious about single points of failure. The article advises ensuring that every application layer, including databases, has regional redundancies. By designing around these redundancies, organizations can effectively mitigate risks associated with outages, fortifying their service availability and reliability. The implications of these updates are significant. As organizations increasingly transition to cloud-based infrastructures, the expectation for uninterrupted service will only grow. The ability to effectively manage multi-region deployments through automation and proactive health monitoring means that companies can focus on innovation and growth, rather than concern about service downtime. In conclusion, the enhancements to Cloud Run for multi-region services represent a substantial step forward in ensuring application availability. As more organizations embrace cloud technology, the emphasis on robust, automated solutions for service continuity will be paramount. Keeping an eye on these developments will be crucial for businesses seeking to maintain a competitive edge. In a world where content consumption is often fragmented, bridging the gap between creating technical articles and getting them in front of an audience can be daunting. This article explores an innovative approach to automating this process. The author has developed a unique pipeline that transforms blog posts into engaging Instagram carousels and YouTube shorts, leveraging artificial intelligence along the way. Understanding this integration can give creators tools to streamline their content distribution. Before this automation was put in place, creators faced significant obstacles in adapting their technical writing for various platforms. Translating a single blog post into multiple formats often required substantial reformulation, including resizing images, rewriting content, and ensuring everything fit the new medium. This manual process could lead to inconsistencies, or worse, no posts being shared at all. Moreover, many creators found their audience scattered across different platforms, often leading to frustration. While a rich blog post exists, reaching the audience effectively required extensive efforts to make use of each platform's unique features. This automation pipeline addresses the inefficiencies, aiming to ensure that content reaches readers without the usual burdens of conversion. The automation pipeline effectively transforms technical blog posts into engaging Instagram carousels and YouTube shorts by creating structured content suited for different platforms. With this system, each blog post is processed and converted automatically, allowing consistent content flow without manual intervention. This shift not only improves efficiency, but also enhances the ability to connect with audiences across multiple platforms. The pipeline operates on a daily schedule, processing one blog post per day. This consistency allows the author to maintain a steady stream of content. Each automated output consists of a YouTube short with a recorded narration lasting around 60 seconds, and an Instagram photo carousel designed specifically to meet the platform's requirements. The carousel format includes diverse card types such as comparison, flow, and takeaway cards, allowing detailed presentation of information. This structured design encourages users to swipe through the content at their own pace, digesting complex ideas without feeling overwhelmed. On average, each carousel consists of 6 to 9 cards, tailored specifically to emphasize key points from the original article. The automation pipeline includes rigorous validation checks before the content is rendered. This ensures that the data being used in the carousel accurately reflects the original article. For instance, any bar or stat cards must be validated against the source. If an inconsistency is detected, those cards are demoted to a less prominent type, maintaining overall content integrity while still ensuring a smooth user experience. A distinctive part of the development process involves utilizing independent reviewers who approach each component without prior context. This adversarial review system is crucial in identifying potential issues that code writers might overlook, ultimately catching 5 significant bugs before the code was executed. This structure pushes for quality assurance throughout the development phase, greatly enhancing reliability. This automation framework not only streamlines content creation, but also sets a precedent for other content creators looking to enhance their distribution strategies. As AI becomes increasingly integrated into daily workflows, we may see a shift in how content is produced, emphasizing the use of structured systems that maximize efficiency while retaining quality. Understanding these trends could lead to significant changes in the landscape of digital content creation. In conclusion, the automation pipeline discussed exemplifies a significant evolution in how technical content can be adapted and shared. This adaptability is essential in a rapidly changing digital world where audience preferences are constantly shifting. As creators explore these innovative tools, they can enhance engagement, reach wider audiences, and evolve their content strategies for success. In a recent article, the authors explore an unexpected challenge in Kubernetes deployments. The core issue revolves around the behavior of config maps and how they impact the automatic restart of application pods. This topic matters significantly for developers managing multi-release architectures, as it reveals crucial pitfalls that can lead to misconfigurations and downtime. Before delving into the specifics of this issue, it's essential to recognize the role of config maps in Kubernetes. Config maps allow users to separate configuration artifacts from container images, making applications more flexible. However, any improper management of these configurations can lead to behaviors that conflict with user expectations, especially in a multi-release setting. In single-release architectures, a common practice is to utilize checksum annotations in deployments. These annotations serve as signals to trigger pod restarts whenever the config map changes. However, challenges arise when dealing with multi-release architectures, where releases are decoupled, complicating how these annotations function across different components of the deployment. The central thesis of the article is that multi-release architectures break single-release assumptions, particularly concerning how Kubernetes handles updates to config maps. When an update is made, the Kubernetes system does not automatically restart pods, leading to potential mismatches between configured values and running services. A critical part of the deployment issue arises from a misunderstanding of how Kubernetes treats config maps. When a config map is updated, it does not change the pod's template spec. Thus, Kubernetes does not register the need to restart the pod. This results in the pod continuing to serve requests based on the previous configuration, not recognizing the newly applied changes. Moreover, for applications that rely on reading configurations at startup without a runtime watcher, this behavior poses a significant challenge. If the application does not implement a mechanism to reload configurations while running, any updates to the config map will remain unnoticed until a pod restart is forcibly performed. The article discusses a proposed solution using checksum/config annotations that can trigger a restart when config maps are updated. These annotations work effectively in single Helm charts where the deployment and config map reside within the same template context. In contrast, when using multiple Helm releases, the current solution demands careful handling to ensure consistency across deployments. A viable approach in multi-release architectures is utilizing Helm file, which supports additional templating functions. This allows for reading configuration files and generating checksums that can be passed across independent releases, thus bridging the gap between related deployments and ensuring updated configurations without manual intervention. The implications of this finding are significant for organizations relying on Kubernetes for deploying services. Understanding how config maps interact with pod lifecycles is critical for ensuring that services consistently operate with the intended configurations, preventing instances of unexpected downtime or service disruption. In conclusion, as Kubernetes continues to evolve, developers and teams should adapt their strategies for managing configurations. By leveraging advanced templating methods such as Helm file, combined with a solid understanding of Kubernetes behaviors, teams can mitigate risks associated with multi-release architectures and enhance deployment reliability going forward. In the evolving landscape of Kubernetes, managing stateful applications has become increasingly complex. An article by industry experts sheds light on the lessons learned while rebuilding a pre-production environment, focusing on two key Kubernetes operators, StackGres for Postgres and Strimzi for Kafka. This discussion is essential for understanding not just the setup of these systems, but their operational implications as they evolve beyond the initial deployment. Before diving into the rebuild process, it's important to understand the challenges of managing stateful systems within Kubernetes. Traditionally, operators faced tedious manual oversight when it came to deployment, especially during complex operations that required constant monitoring for backups, recovery, or scaling. Standard configurations often left gaps in automation, leading to increased operational overhead and potential downtime. As organizations increasingly rely on applications powered by data, robust solutions are vital. For instance, many systems utilize Postgres MSQL for storing time series data, while Kafka serves as a powerful event streaming platform. Transitioning these systems to a more resilient architecture using Kubernetes operators like StackGres and Strimzi holds the potential to streamline operations and improve reliability. The central thesis of the discussed article highlights that utilizing Kubernetes operators such as StackGres and Strimzi profoundly enhances the management of stateful systems, particularly concerning DAY2 operations. These operators not only simplify initial setups, but provide critical automations and recovery mechanisms that can dramatically reduce the risk of human error during operation. A fundamental aspect of operators, as outlined in the article, is their ability to encode operational knowledge into a controlled environment. For instance, with StackGres, users can declare their intentions for a PostgreSQL cluster with precise configurations, such as wanting 3 replicas. The operator takes over management tasks, continuously reconciling that state. This contrasts steeply with Helm charts, which oftentimes fall short in continuous monitoring and adjusting. Backup management stands as a prime example of this advantage. With StackGres, administrators can define backup configurations declaratively, allowing the operator to handle lifecycle management automatically. Tasks that previously required extensive manual intervention can now be succinctly defined. For example, when configuring backups, there's no need to write custom scripts or set up cron jobs. Simply declaring policy suffices, making the process less prone to failure. Further showcasing the operator's capabilities, the article recounted a dramatic instance involving a replica in a PostgreSQL cluster encountering failures. Instead of navigating a complex manual repair process, the built-in fallback logic of StackGres offered a clear and quick reinitialization path after a failure. This contrasts sharply with previous methods, where system recovery often involved error-prone manual interventions. Strimzi, the operator for Kafka, also highlights these operational advantages. Managing Kafka clusters through a custom resource definition, Strimzi automates critical tasks like certificate management. It facilitates rolling restarts, ensuring that Kafka services remain resilient and secure without manual oversight. Additionally, certificate renewals are handled seamlessly, automatically rotating certificates while maintaining service continuity. The implications of adopting Kubernetes operators extend far beyond individual clusters. As organizations continue to grow and scale applications in the cloud ecosystem, embracing these technologies can lead to a paradigm shift in operational excellence. The ability to streamline processes and minimize potential outages aligns well with the increasing need for businesses to deploy reliable, data-driven applications in competitive landscapes. Reflecting on the considerable benefits highlighted by the article, it is evident that operators like StackGres and Strimzi are essential for any organization looking to manage stateful applications effectively. Their operational efficiency not only enhances reliability, but also fosters a proactive approach to potential challenges that may arise post-deployment. Operators are certainly reshaping how we think about operational resilience in Kubernetes environments. In the realm of AI and cloud infrastructures, the latest innovation comes from Databricks, which has introduced Omnigent, a tool set to redefine how we manage AI agents. This article explores the significance of Omnigent, often described as a meta-harness, and its implications for both infrastructure engineers and organizations leveraging AI technologies. Before the release of Omnigent, managing AI agents involved a lot of manual configuration and siloed tools. Engineers had to navigate individual agent harnesses, each with distinct APIs and management requirements. The lack of a standard interface made it cumbersome to switch between agents or share context, leading to inefficiencies and potential security risks. Infrastructure teams are accustomed to deploying services on platforms like Kubernetes. However, when it comes to the agent layer, similar orchestration challenges remain unresolved. For example, deploying AI agents often raises questions about state management, policy enforcement, and network boundaries, issues that Omnigent aims to tackle through a more cohesive framework. The core thesis of the article identifies Omnigent as a revolutionary solution that provides a common API for various AI agents while addressing deployment and policy management challenges. This unified abstraction simplifies interactions between different AI models and allows organizations to enforce consistent policies across their agent implementations. One of the key features of Omnigent is its structured approach to session management. The system identifies runners that encapsulate agents in sandboxed environments. This ensures that all agents can operate independently while abiding by the defined policies without modifying the underlying agents themselves. The runners handle network requests and apply security policies effectively. Omnigent employs a robust server architecture that manages sessions, policies, and sharing across agents. These policies are not merely simplistic allow/deny lists, they are stateful and contextual, allowing for complex rules such as requiring human approval for actions based on the state of the session. By fine-tuning agent behavior through policies, organizations can develop a sophisticated risk management strategy. When deploying Omnigent on Kubernetes, the choice of database becomes critical. While SQLite is suitable for local setups, it offers limited persistence, risking data loss when pods restart. The article suggests using a managed Postgres database, which is not only more robust but essential for production environments. Postgres allows for proper data handling and supports multiple replicas, enhancing reliability. The migration process for setting up a Postgres instance is also streamlined. The initial migration takes approximately 1 minute, provided you account for startup probes. Understanding this migration timeline is crucial for avoiding unnecessary downtime during deployment. The presence of a timely migration ensures that teams can move to production smoothly without facing operational hiccups. The introduction of Omnigent signifies a broader trend towards enhancing the structure of agent layers within cloud infrastructures. As companies shift towards increasingly complex AI systems, tools like Omnigent are critical for ensuring that security and governance necessitate contextual awareness, enabling organizations to define and control their risk models effectively. As more companies adopt advanced AI solutions, the question remains: will organizations take the leap to fully define their security and operational models, or allow default settings to dictate how their agents operate? The choices made around tools like Omnigent will undoubtedly shape the future of AI deployment and management. In a recent exploration of Kubernetes, an insightful article highlights a challenging pitfall developers may encounter when deploying applications. Written in a personal narrative style, it discusses a specific failure while trying to deploy a Django app to a Helm lab cluster. This revelation matters as it exposes a nuanced discussion around environment variables, their injection mechanism, and how they can lead to confusing and frustrating runtime issues. Before diving into the particulars of this failure, it's essential to understand the broader landscape of service deployment within Kubernetes. Kubernetes uses an environment variable injection feature that allows applications to discover services dynamically. Many developers, especially those adhering to 12-factor app principles, might assume that environment variables will reflect their defined configurations without unintended consequences. The core issue presented in this article revolves around how Kubernetes environment variable injection can inadvertently cause conflicts in applications designed with 12-factor principles, leading to unexpected failures. The narrative reveals a specific instance where a Redis connection string was improperly formatted due to this environmental variable injection, highlighting an easily overlooked incompatibility. Upon deploying the Django app, the initial green indication of successful pods gave no hint of the underlying issue. However, as the author attempted to log in, they were met with an HTTP 500 error. This wasn't a simple one-off failure. Every view that interacted with the cache produced similar errors, signaling a systemic issue tied to the environment context. The health check remained operational, but the core functionality was compromised. A pivotal moment arrived when detailed debugging inside the pod revealed that the application was attempting to establish a Redis connection using an incorrectly formatted URL, tcp://10.233.61.42:6379. Originally intended to be a simple connection string, this construction stemmed from Kubernetes injecting the Redis_port variable, demonstrating a direct conflict created by Kubernetes' built-in mechanisms. The article outlines how this unexpected formatting led to a runtime value error, ruining the environment's operation. Kubernetes dynamically injects environment variables for services at pod startup, including a host and service port. However, if a service is created after a pod launches, the corresponding variables will not be available. This means a previously functioning deploy can suddenly break if there are changes in service names or availability. The author's experience emphasizes this point, outlining how their Postgres connection remained unaffected merely by chance due to different variable naming conventions. The article identifies 3 potential solutions to mitigate this issue. The most effective solution was to disable service link injections through the pod spec. However, if modifying the pod spec isn't feasible, explicitly setting the Redis_port variable can serve as an alternative fix. This workaround shadows the injected variable, though it's a site-specific solution and does not address the underlying mechanism that might trip future deployments. While the article primarily details the issues arising from this environment variable injection, it does leave open some potential alternative views. One might argue that this type of variable collision can be avoided with proper naming conventions or practices. However, the author remains skeptical of this notion, feeling these conventions depend heavily on developers' knowledge that may fade over time. This article serves as a timely reminder about the complexities of automated environments in contemporary deployment practices. When automated systems like Kubernetes maintain legacy compatibility features, it can introduce unexpected behaviors for applications that assume a smooth operational environment. Developers must remain vigilant and incorporate thorough debugging processes as a part of their workflow to uncover such hidden issues. In a world of rapid technological advancement and frequently evolving best practices, keeping abreast of such compatibility behaviors in platforms like Kubernetes is essential. As developers, being proactive about potential pitfalls can streamline the deployment process and ensure continued application functionality, even as the ecosystem continues to evolve. On June 30th, 2026, Anthropic released Sonnet 5, a successor to Sonnet 4.x. This upgrade has sparked curiosity around the differences in performance and capabilities, especially considering the absence of detailed architectural disclosures from the company. This video delves into the findings surrounding Sonnet 5, exploring its benchmarking results and the implications of its advancements in generative AI. Before the launch of Sonnet 5, the landscape was dominated by models like Opus and Mythos, setting high-performance standards in generative AI. Sonnet 4.6 was a key player, but users often found limitations with its capabilities. This backdrop created significant anticipation for any advancements that Sonnet 5 would introduce, particularly as AI applications evolved and demanded greater utility. The core thesis of Sonnet 5's release is clear. It demonstrates significant advancements over Sonnet 4.6, particularly in its benchmarking results, despite the lack of detailed technical disclosures regarding its architecture. The improvements hint at enhanced capabilities across various benchmarks that measure real-world performance, setting a new standard in generative AI. One of the most striking improvements is Sonnet 5's score of 79.5% on the USA MO 2026 benchmark, a substantial increase from Sonnet 4.6's 55%. This benchmark, designed to evaluate proof-solving capabilities, indicates that Sonnet 5 can effectively tackle complex mathematical reasoning tasks. Such a leap underscores the model's progression in understanding and constructing proofs, which is crucial for applications requiring high-level reasoning. Sonnet 5 also achieved an ELO score of 1618 on the GDP Val AA v2 benchmark compared to its predecessor's 1395. This metric illustrates its enhanced performance on complex professional tasks. ELO scores provide a nuanced understanding of a model's capabilities, revealing that Sonnet 5 is now much more adept in real-world applications, indicating an ability to compete in more advanced scenarios as it narrows the gap with leading models. In terms of software engineering tasks, Sonnet 5 performed remarkably well on the SWE Bench Verified benchmark, scoring 85.2%. This score means that it was able to produce correct patches for around 5 out of 6 real bugs from GitHub repositories. The previous best score was around 65%, showcasing a significant leap in its coding capabilities and reflecting a model that is increasingly capable of functioning as a coding assistant in real-world environments. Another noteworthy benchmark is the HLE, Humanities Last Exam, where Sonnet 5 scored 43.2% without tools and 57.4% with tools. The increase from 44.2% to 57.8% for healthcare-related queries indicates meaningful improvements in the model's capacity to assist in clinical reasoning. As AI continues to penetrate domains with high stakes, such advancements are critical. Additionally, Sonnet 5's performance on the terminal bench was also impressive, achieving an 80.4% score. This benchmark measures the model's ability to carry out real Linux or Unix terminal tasks, underscoring its practical applications for system commands and scripting. This level of proficiency indicates that Sonnet 5 is well suited for environments where users interact directly with command line interfaces. The advancements in Sonnet 5 highlight the accelerating pace of improvement in generative AI. These benchmarks suggest that as models evolve, they are increasingly capable of handling complex, real-world tasks that were previously a challenge for AI. This evolution not only impacts the tech industry, but also sets a precedent for future developments in AI, pushing boundaries in automation and AI-assisted workflows. In conclusion, while Sonnet 5 does not disclose specific architectural features, its benchmark scores illustrate a marked advancement in capabilities and performance over Sonnet 4.6. Moving forward, the AI community should remain vigilant about the evolving capabilities of these models, as they shape the landscape of AI applications and influence how users interact with algorithms in their daily tasks.